I hope you can all hear me. So thank you all for coming today and to the presentation of Professor Agioutantis. It's a great honor and great pleasure to have Professor Agioutantis with us today. I just want to make a short introduction about Professor Agioutantis for those that they are not familiar with his background. Actually, Professor Agioutantis used to be a professor at the Technical University of Crete at the School of Mineral Resource Engineering for more than 2 decades, and he was the director of rock mechanics lab. And then he moved to the US, to the University of Kentucky, and now he's the chair, he's professor and chair of mining, of the Department of Mining Engineering. And today he's going to give us a talk about software that he has developed. The software is called Wetbud, and it's in general, it's about hydrological design of wetlands, which is a very interesting subject, both for mining engineers and generally for environmental engineering. So after this short introduction, I would like Professor Agioutantis to welcome you again, and thank you very much for accepting our proposition. It's a great pleasure to have you. So please, the floor is yours.
Thank you. Okay, as Emmanouil said, I am Zach Agioutantis. I'm currently a professor at the Department of Mining Engineering at the University of Kentucky, and I've been serving as the chair of that department for the last 5 years. And I have been here at TUC for 25 years. I left TUC in 2014. This is a work that was done as a collaboration between 3 universities in the US, and it's a multi-partner and a multi-year project. It's not really, when this work started, it wasn't really related to mining, but Emmanouil and I had an opportunity to actually apply to mining applications. Let me just put this in front of you, just keeping in mind, because I'm going to be talking about models, and all models should be taken with a grain of salt. You know, students are typically fascinated by colors and nice contours of red, green, black, or whatever, but you always need to check your numbers and check your data. So what is Wetbud? Wetbud is actually, comes from 2 words, wetland budgets. So it's wet from wetland and bud from budgets. It's a free tool for the design of constructed wetlands. And it's designed to help engineers, scientists, and wetland restoration professionals to calculate and analyze water flow and eventually design a wetland. So why do we need to design wetlands? Before I answer that question, let me say a few things about Wetbud. Wetbud uses 2 types of models, an analytical type of model with sums in, water in and water out, and produces monthly charts of typical years, and a graphical interface to a very well-utilized software package, which is called ModFlow, and it's developed by the United States Geological Survey. ModFlow is a free package, so Wetbud actually provides an interface to that free package. So Wetbud was developed for wetland mitigation banks. So what is a wetland mitigation bank? When somebody needs to build a road and destroy a wetland, at least in the US, they need to develop another wetland in that area to make up for the lost wetland that they destroyed. So when we built the road from the bus station to this department, we destroyed so much area of, it wasn't a wetland, obviously, of natural habitat. So we should have, or the state should have provided for a replacement area where that natural habitat would be restored. So wetlands can be, wetland mitigation banks are areas where people develop wetlands, and then somebody can buy that area to account for land that was destroyed because of farming, because of a road, because of whatever other projects that they do. Now, Emmanouil Varouchakis and I have found an application to design wetlands for mining applications, whereby we use wetlands to clean the wastewater that comes out of a mining processing facility, tailings facility, using the plants to do phytoremediation on the water. That's a side sort of application. The main application was wetland mitigation banks. So basically, you start out with an area that has nothing, and then you need to create a mitigation for that area to compensate for what we call permitted impacts. So we're going to create a subdivision, a housing area, and you destroyed some of the forested wetland area. Somebody needs to create a wetland to compensate for that. So when I talk about mitigation site, is the site we select to create another wetland. So a poor mitigation site is a site which is not really good for that type of application. It doesn't have a floodplain. Now, does everybody know what a floodplain is? No, you do? Who doesn't know what a floodplain is? Okay, floodplain. So when you have a river, and that river, the water sort of rises, it will cover an area around that river. That's a floodplain. So if you do not have a floodplain, it's difficult to accumulate water, and that site is probably not a very good mitigation site. If you have a lot of existing wetlands in that area that take up a lot of water, again, that site may not be a good mitigation site. If you have a lot of streams that would flood your wetland area, that may not be a good mitigation site. Now, a wetland, I didn't put the definition here. A wetland is defined as an area that may be wet 9 months out of a year. So you have all the bugs, the mosquitoes, the flies, and all the other living creatures develop in water, but it will dry out for 3 months out of the year so that these creatures can actually multiply under dry conditions. So it needs to have both dry components and wet components. That's how a wetland is different than a lake. A wetland may be something like a swamp, but not a lake or a river or a stream. A good mitigation site, you need at least 20 acres. 20 acres, 1 acre is 4,000 square meters. So 20 acres is whatever that number is a big area. You need to have soils that do not drain, because you need to keep the water there, and with an easy access to a floodplain, so you can actually get that water into the wetland, and that water stays there. So, as I said before, this was a multi-year, multi-partner project. There were a bunch of people that worked at Virginia Tech. Virginia Tech are the red letters there, Professor Lee Daniels and Professor Tess Thompson. There was also a bunch of students that got their degree at Virginia Tech. It says undergraduate students, the ones in red. There's another university in the state of Virginia, which is right at the Atlantic coast. It's the Old Dominion University. There was a group of people working there as well. And I did all of the programming and a lot of the implementation of Wetbud through the University of Kentucky. So I am the programmer behind this package. A lot of other people developed the information that goes into this package. Just to give you an order of magnitude, this package has probably over 500,000 lines of code, for those of you that do coding. This presentation, a number of Wetbud presentations have been given over the years, and this presentation draws from several other presentations. Sometimes I have acknowledgements behind every slide, below every slide, and other times I do not, but it actually draws from all the presentations or many presentations that have been given over the years. Okay, so what is Wetbud? That's the main menu for those of you who have seen that, and I'll show you how to download it. Like I said, it's a free package. It's a database driven. I'll explain that in a few minutes. It's a Windows application. It doesn't run on a Mac. And it has a database which can be shared between users. What you can see here is the main screen of the program, and this is actually a picture of a wetland. You can download Wetbud out of the site, which is called resourceprotectiongroup.org/Wetbud. And there's a menu item here that says Wetbud software download. You enter your name and email, and you can download the software. Many sites were considered when developing the package in terms of analysis and testing. These sites are all located in the East Coast of the US, states of Virginia, perhaps Maryland, North Carolina, but they're located around that area. There's a list of 8 sites here and the people that did the work in each of these sites. Just to give you some reference, Washington, D.C. is about here where my cursor is. Yes. This is the first wetland that was developed under this program. This is the Julie Metz wetland. You can see, standing water here, and this is in the spring, so we have a lot of vegetation, but you can also see trees. So again, this ecosystem has a specific design behind it so that it can keep the water during the wet periods, but it can also dry out during the dry periods. So what's in a water budget? A typical water budget will have the following components: precipitation, which is rain; any surface water input, which means it rained over here and the water came on to my area of interest. It flowed on the surface and rests now on my area of interest. There's groundwater that comes from the side. So surface water, groundwater. Groundwater travels underground. There is water if I have a stream in the proximity of my wetland, like you see here on this sketch. Then there may be water overflowing that stream and feeds into my wetland. These are, I would say, gains. So these are positives, and you can see P+++, so 4 items that contribute to my water budget. And then I have losses. So my losses are ET, evapotranspiration. That's the amount of water I lose because of the sun and as the plants breathe. So that water is lost. I have water that runs off my wetland. I have water that runs on the surface, runs off, goes out of my wetland through the ground, the horizon that's under my wetland. So I need to know the permeability and everything for that soil layer. And all of that basically makes up what stays in the wetland as net storage. So the wetland will store some water after we add up the contributions and we subtract the losses from that budget. And you can see here with the different arrows: surface water, stream overbank, that's inflow; ET, that's a loss; precipitation, that's a gain; and groundwater in, groundwater out, and then outflow over the little weir that has at the end, and then the rest is storage. Any questions so far? Okay. Now, in the old days, and that's pre-2010, it was a very simple model. We assumed this was 0. Okay. And as you see, there's only two components, one in, one out from here, inflow from like surface water, and then the rest outflows and some stays in the wetland. That's a very simple model. This guy. Now, a runoff is calculated by I guess, an equation that's given here. I'll show you that equation later. But that's a way, there's an easy way to calculate runoff based on precipitation. So it rains over here, that water hits the landscape over here, hits the watershed, and then runs into the wetland. So that there is a formula to calculate that. There's another formula to calculate ET. There's multiple formulas to calculate ET. I'm not sure how to get rid of that.
Throw shift up H.
Say again?
Throw shift
Throw shift.
up H.
Okay. There's multiple formulas to calculate ET. This is the Thornthwaite equation, which does a monthly ET estimation. It's an estimation. We estimate that in July of this year, in that area, we will have so much water lost due to evapotranspiration. And for precipitation and for wetland design, we need to account for 3 years. What we call a dry year, and I'll explain what a dry year is, what we call a normal year. So D stands for dry, N stands for normal, and W stands for wet. So what we anticipate to be a wet year, okay? And anything that, if we have more water, and that water goes over the weir is a small dam at the end of the wetland. It will go over the weir, consider that outflow, the rest stays into the wetland, and it's storage. So that's the old traditional way. You could do that in a spreadsheet. Now, what if we want to add overbank? The traditional way didn't know how to deal with overbank. So remember, overbank, we have a stream that's dumping water in a wetland. What if we want to have other ET estimators, like Penman, like Bowen's ratio, like you have an ET measuring device and you have data that you collected and you want to put it in there? You couldn't do that with the old method. What if we want a standardized D&W calculation so that everybody uses the same years for the same location? And what if we can adjust, or we want to adjust, the weir elevation to account for flow rates? So in many areas like that, even in rivers, you have gates. If you have a lot of water, you may want to open the gates, let some water out. If you have less water, you want to close the gates to trap some water into the area. And what if this line on top of the wetland, because of flow, is not flat, but it's tilted, so water actually flows from your left to your right? Here's an example. Let's say, and you can see the topo file here, you can see the surface contours. Let's say that we have we want to construct a wetland here. We have an existing wetland, which is highlighted by that. This whole drainage area, by drainage area, I mean, if it rains within that shape, all that water is going to come down to our wetland area. So this is our drainage area. And we want to have so much depth of water in that specific location. So that's where we start. We start with a map. We say, here's a wetland. We want to expand that area, double the capacity or whatever. And what is involved in that process? So the guys that started this process were two people. One was Gary Pierce and the other one was Mal Gilbert. Actually, Mal is still teaching courses in different universities on how to design a wetland, and he uses this package. The end result, and I'm going to go over this again in my examples. The end result would be something like this, where each bar corresponds to either an input or an output. Inputs are positive on the positive side of the y-axis, and outputs are on the negative side of the y-axis. For example, this purple bar here is PET lost in July. Yes, in July, there's a lot of sunshine in the northern hemisphere, so we lose a lot of water. That's why PET is high. At the same time, however, in that area, in some of these areas that I showed on the East Coast, in the summer, which is different than what happens here in Greece and Hania, in the summer, there's a lot of rain. So yes, in July, they have a lot of rain. So actually, they have the most rain than they have in February or March. So high precipitation and so on. Okay, I mentioned in the beginning, we have two models. The basic model, which I will call the bathtub model. So you have a bathtub, and you want to fill the bathtub, and then you sum up the ins and outs. So that's the model up here. Even with the extended ins and outs, it's a bathtub model, it's a black box. And then you have a model where you actually know your soil layers, you know your topography, you know the thickness of each layer and the composition, the ground soil composition, so you know the permeability. And therefore, you can calculate head. Head means water elevation, water pressure for every cell. So a basic model will do this, an advanced model will do this. All of these inputs here that you see, ET, for example, or precipitation, are what I call time series data. Do you understand what I mean by time series? Could you explain? Changes over time. So you have precipitation in January, February, March, which are different values, and you may have 30 years of time series just for one variable. 30 years, 30 monthly values, and if you do daily, you have 30 times 365 for one variable. Same thing for ET. Same thing for any of the other variables that are involved. That is why I said initially that everything is stored in a database, so we can easily retrieve those time series and work with them. Any questions so far?
Why WDI?
Weir. Okay. So a wetland is like a bathtub, but on one end of the bathtub, there is a little damp phragma that you can actually regulate its elevation. So by regulating the elevation of the weir, you can keep water in, or if you lower it, water will flow out. So weir is a small dam structure that's at the end, at the outflow location of the wetland. Okay? Yes.
Regarding the parameters that you are taking into account, what about the condensation of the water?
What do you mean by condensation?
I mean the water that is in the area and becomes liquid on the surface of the wetland.
If you have high humidity.
Yes. And then the temperature changes.
This is not taken into account directly, but if you use ET through local measurements, that will be incorporated there, because that actually returns into the area. If you use ET through theoretical formulas, that's not taken into account. But we can use ET through user-defined measurements. Evapotranspiration. Any other questions?
Apart from the small dam that we start at 1 air,
I mean, is there another way like clay barriers that you can do in order to stop the loss of water behavior and everything?
Okay, good question. So, let's see if I can actually make this larger. Okay, so this is a conceptual sketch of a wetland. Okay. Okay, here's the wheel. Okay, that's a little channel that actually controls outflow. This is a stream that may contribute to the water if there is enough water to go over a little channel that's there, or if the stream actually floods because there's a huge flood, water may actually come over this berm. Berm is a anachoma. Okay. Now, when you construct the wetland, you can actually specify how thick your soil layers are going to be and what soil you're going to put there. The basic model cannot utilize that information. The basic model only uses an average permeability K value for the whole wetland bottom. The advanced model, however, you can specify layers. You can say this layer is 15 centimeters high, and this is another 15, and so on. Okay, good question. Any other questions? Okay. Let me go back to this. Okay, so data needed. In the United States, there is the National Oceanic Atmospheric Administration, NOAA, that collects a lot of data from many locations. Typically, I mean, right now, there may be over 9,000 stations. These stations are mainly in the US, but there's also worldwide. The link given here actually takes you to their website, and you can click on stations and see their data. Okay, so that is how we get historic rainfall precipitation data for locations around the US. This is a map of stations. These stations are typically located at airports because airports need good weather models because of aircraft flying in and out and safety. So aviation safety. So this is a map of where these weather stations are, and we get precipitation. Oops. Now, when this project started, it started from the Virginia area. So some of the graduate students that work on this project, this is the state of Virginia. This is the Atlantic right here. This is Washington, D.C., just to give you an idea of where that is. So they divided the area of Virginia, state of Virginia, into, I think, 12 regions, according to the morphology of the ground and other and weather patterns that they could find. They did that in GIS. And they assigned a representative weather station for every region. So, for example, in this region, this is the Roanoke Municipal Airport. This dot represents weather for this region. This region, this is the Richmond International Airport, represents weather in this region. So if and I will do that in a minute when I do a live demo. If I specify that I want to build a wetland in that area and I give the latitude and longitude of that area, it will automatically grab that station and say, this is the nearest station for which we have data. It's recommended you use that station. Now, you may not use that station. For example, when Yanis and Michalis did their diploma work, they used a location in Chalkidiki. There was no weather station. So they created their own weather station. They populated their own weather station with data, and that's what they used for the analysis. Okay. So the state of Virginia was the initial, the work done there was to divide that state in 12 areas. That was the initial work. Right now, we have in our database 140 weather stations that span all these areas in the eastern US. And there's also some that are in the central and western US, but we call these preloaded weather stations. So each of these stations has 30 years of data, 30 years of daily precipitation data, which is a lot of information because that information has been sort of vetted. Vetted means we have looked at the information. All points are there. There's no missing dates. There's no zero values. I mean, if it's zero, it's an actual zero. Sometimes the station is broken and we get a -99, which means no value. We have cleaned all this stuff up, and this is provided again with the Wetbud package. So these two pictures, this shows the locations and influence areas. And these show basically the physiographic provinces. So this is where we have the different soil layers and different morphology, the mountains and the plains. And this shows the precipitation patterns. So this is, for example, a case where we say, okay, we want to locate a wetland in this area. The program will prompt and say, yes, I have this station, and for this station, I have precipitation. I also have ET calculated by the Penman method. I have ET calculated by the Thornthwaite method, and all of that. And you can choose whatever, because I have all the data that you may need. You can choose whatever you want. Okay. And then if you click on that link and say, where is my project? Here's my project right here. And the nearest station will be that one. Okay. And now, like I said, I'll do a live presentation in just a bit. Now, I talked about the dry, normal, and wet years. So this is important because you need to do, you need to anticipate very wet years, high precipitation. You also need to anticipate very dry years. If you do not anticipate your dry years, your wetland is going to die. If you do not anticipate your wet years, your wetland is going to, be flooded, and it doesn't function as wetland anymore. It's a lake. So to define those dry, normal, and wet years, we used what's called the WETS tables. So WETS tables, again, is something provided by NOAA, the National Oceanic Administration. And what they've done is they've done statistics on the precipitation data. And I'll show you what are these statistics. So they would take, for example, a given station. They have data for 30 years, 1971 to 2000. For January, this is their average daily temperature maximum, average daily minimum. So this means in January, over 30 years, the average maximum temperature was 35.4. This is in degrees Fahrenheit. The average precipitation was 2.53 inches. Same thing for February, March, and so on. And then, so they have the statistics, and then the next thing they did, I have it here. This is the annual total. But look at this, it says there's a 30% chance that they will have less than 35. And there's a 30% chance that they will have more than 41. So they've looked at 30 years, and then they assign probabilities. 30%, we have less than 35. So that you start thinking, oh, could be a dry year. And then 30% chance that we will have more than 41 inches of precipitation a year. Multiply by 2.5 and you get centimeters, or by 25 and you get millimeters. And then there's a 40% chance we're in the middle that we will have a normal year. So we use these tables with a procedure to calculate dry, normal, wet years. Now, the guys that did a thesis on Wetbud did not have that information because there's no wet table for the array. Okay, there's not enough. But if you had 30 years worth of data, you could have done that. So we go, Kali, what did you say? Shift
Up.
H. Okay. Oops, again. So for a given weather station, this is my dry period, this is my 30%, this is my wet period, this is my 30%. So with that, if I get the median of that, you know what the difference between the median and the average is? Everybody knows that? Okay. If you get the median year corresponds to 1988. So for that station, I would say that my dry year, I would use the 1998 precipitation values to represent my dry year. And I would use the 1994, which is the median for this area, for this span, values to represent my normal year, and so on. But I do another check too. And the other check is I give it a score if I have a wet spring or not a wet spring. And the wet spring is important because remember, a wetland, you need to have those bugs, loosely talking about bugs, I mean, you can call them anything you want, multiply. So you need a wet spring for the bugs and the mosquitoes and all that to multiply. So you would check if that year has a wet spring or not. And if it doesn't have a wet spring, then you will go around the median until you find a year with a wet spring. But the procedure it's pretty automated in Wetbud, and therefore everybody will use the same dry, normal, and wet years for a given. Okay, basically what this says is in the old times it would be BPJ, best professional judge. So you come to me and say, what is the wet year for Hanya? Ask Andreas, what's the wet year for Hanya?
2019.
2019. Why? Because you were here in 2019 and it was bucketed. Okay. But I was here in 2004 and it was even worse. You were not there. So everybody can give a different answer. Okay. Or I could run statistics, but are you going to run regular statistics, median statistics? What are you going to do? Or use a properly defined process, which is this. Okay. I've gone over that. And the last thing I want to mention here is that this is for relatively flat systems. Okay, the basic model applies to relatively flat systems. Now, if we want to go beyond the PIRST model, which is the bathtub model, then we need to consider groundwater input. It's very important. Overbank flow. I'll talk about storage curves, and I'll talk about reference hydro periods. So let's do groundwater input. Okay, then I will start with a question. How would you know how much water would come from the side into a wetland? So if I go back to this diagram that I showed you before, this is runoff. Runoff is water on the surface that actually goes into the wetland. Where would groundwater come from? Anybody? Groundwater input, not output. Output is easy. You have the bottom of the wetland, water drains down. Here, in this diagram. Where would groundwater in come from?
Maybe, I'm not sure. When we have rain, the water table in the ground goes up.
Correct.
So then in this question, there is no component of this water that goes in.
Very close. So it depends on the piezometric surface. Okay. So groundwater in this case, it would come from here. It would come from the side, this side of the wetland. It may come also from the bottom, but it will come from the side. Okay. Going back to your hydrogeology classes. What is the equation? Which equation relates movement of water to head?
Zero.
Very good. So we utilize the groundwater input. We use Darcy's law for groundwater input determination. To do that, we need two wells, geotrices. We need two wells. One, this is a wetland, one uphill, one downhill. We measure water elevations in these wetlands, in these wells. We have the distance between the wells, and now we can apply Darcy's law, difference in elevation over the distance, conductivity and area and all that, and estimate how much water may come into the wetland. Okay. But what if we do not have water measurements for that area for 30 years? And we will not have water measurements for 30 years because we decide to do a wetland here. Oh yeah, let's put two holes in and we'll measure water for the next couple of years. So we have 2 years. Can we do that? The answer is yes. So researchers from ODU, the other university, not Virginia Tech, not Kentucky, the Old Dominion University, came up with this formula that calculates what we call the monthly risk charge, and is a function of these parameters. I won't go into the details, but I'll give you a qualitative explanation. Basically, if we have 15 monthly measurements between two wells, we can calculate, we can predict either back or forward. And what we're interested in predicting is we need to have values for the dry, normal, and wet years, because we will use values for precipitation for those years. We will use values for ET. We need to have groundwater. We need to have WEM values, be able to estimate for these 3 years. All we need is 15, at least, see, we can do with 12 actually, but we need about a year of measurements. This is an example using the WEM method. The green line is the observed, and the red line is the predicted elevation of these two wells using that methodology that I just described. And that's also a functionality of wet. So if we have the data for the wells, we enter the data of the wells, we need the distances, we need the different elevations, and then we run the model and we can have an estimate of groundwater input for that area. Any question? Okay, yes.
You mentioned quite earlier that the data you use from the stations may have some gaps that the program corrects.
These have, good question. We downloaded data from NOAA, and the grad students working on this project went through every month, made sure all the data were there. If data were missing, they would go to neighboring stations and try to fill in the gaps.
Yeah.
So the data sets in Wetbud are complete. Now, if you decide, but the data set go up to 2015 or whatever. If you want to do a 2022 year and the year is not there, you have to do this manually on your own. That's what these guys did. This is the publication for that explains the WEM methodology for groundwater. So basically what this does, it does a multi-parameter iteration process. It gives you the best coefficient of R square right there. You click on the R square, it gives you the equation, and you can use that equation for that. And I'll show you that. So I'm going to skip over these to go to overbank flow. So overbank flow, this is a wetland. Okay. This is the wetland watershed. It's a watershed. What's a watershed? Don't know what a watershed is. So this is the watershed, Lagania Boreis, that feeds the wetland. Okay. But we may have a different watershed that feeds into the stream. Okay, so this is the wetland watershed. This is the stream watershed. Two different areas. Okay. Now, we use the wetland watershed to calculate what? Runoff. Precipitation is what goes into the wetland directly from above. So precipitation is the amount of rain that goes into the green area. Runoff is there's rain going into the blue area here. Some of it will infiltrate and some of it will actually run on the surface. Okay, this is runoff. This is also an input to, this is surface flow that goes into the wetland. Okay, now, same thing happens in this bigger watershed. Precipitation goes in it, there's runoff, and that runoff concentrates and gets into a stream. So we can calculate how much water, again, this is in the same area. So we know how much it rains. And we know how much it will rain in a wet year or a normal year or a dry year. So we calculate how much water will get into stream watershed. We know the dimensions of the stream. We can calculate how much water will go into the stream and eventually how much water will inflow into the wetland. Now, does anybody remember what the typical rain curve looks like? It rains, it starts raining. It rained the other day here. It was mud rain, but what's a typical rain curve? There's a peak, there's a tail. Okay. So Wetbud includes a type 2 curve, which is a typical curve for rainfall, is built into Wetbud. So it will take all this data, fit it to a type 2, and it will give you runoff and time of concentration and all that for the specific stream watershed. Okay.
Quick question, man. Here we assume that the two watersheds are actually represented for the same rain station.
Yes.
What if it's in the next? Is it a problem or?
The water stations, the regions are very large.
So interesting, sure, yeah.
Yeah.
Because let's say in Greece, we may have small watersheds in like even in Crete, we have around 80 watersheds. Some of them are really small, some of them are big, but so if I define a rain station, we don't have so many stations, but what do you have neighboring?
This actually never came up. That's a good question. If we have an application for that, we can.
Yeah.
Yeah. Any other questions? Okay. Yes.
Given that most of the data that you showed is based on US measurements, and based on the question of the professor that the transition, let's say, from the US measurements and let's say increase, do you find it would be a transfer of data from, let's say, US measurements to European or
Yes.
measurements?
Yes. You need to have data for the specific area.
If you can provide, let's say, a model for which the data should be collected to the region where the wetlands.
The model is going to be the same because the way rain works and runoff is the same, but you need to have a time series that corresponds. If you want to do a study in Lamia, for example, you need to have data from Lamia. You cannot use data from Thessaloniki.
The only reason why I'm asking is because you said that in the GIS, you can put the longitude and the latitude, and you can find the specific measurements in
Yes.
the US,
Yes,
but that will give you a result based on US.
on that region,
On that region,
yes.
but you shouldn't take this sample and tell.
I'll show you, good question, I'll show you in a few minutes when I do the live presentation, yes.
Follow-up question. In our case, for Hanya, we have found out that type 3 fit the distribution better. If I remember correctly, there in Helsinki, they got the gamma, I think, gamma function.
Yeah.
That's where but have the functionality to use a different distribution program.
No, right now, no. Right now, no.
Can we use anamorphosis to move from to transform back to data
Yes.
function?
Yes. Any other questions? Okay. Now, going back to Maria, you asked what the weir is. So we have a weir right here. That weir is for outflow of the wetland. We also have channels that may be used to feed the wetland with water. Those channels also may have a weir. So the program allows for input weirs. And there's three different methods here, these three weirs that can be used to control input into the wetland. And I'll show you that in a few minutes. Again, it's the same. So this is, it says here, outflow weir. It says inflow weir or channel. So the red arrow corresponds to a weir that we put there to allow for water to come from the stream into the wetland. Okay. Okay. And this is your question.
That's a question about the line.
That's fine.
Is it much?
Yeah.
For me, it doesn't.
Yeah,
Do
well,
have.
it's a bit much. We can't put it.
Let me see.
Yeah, now.
So this is a cross section of this area right here as an input weir. This is the input weir. And we can actually model that as a cross section there. This input weir, which is right here, we can model that. So the water from the channel, from the stream, we calculate the flow, and then that flow is going to get into the inflow weir. And again, we'll measure how much that's going to get filled, and we can calculate how much water we get into the wetland. This is all water balance, but it's restricted by the specific geometry of every channel that we have. And these are the different elevations that we have. Elevation of the berm, so water doesn't go off the berm, elevation of the bottom of the weir, and so on. And we have analytical solutions for all these cases. So this is a stream, and this is the floodplain of the stream, and how much water gets in, and then eventually how much water will overflow into the input weir. So this is a very, I would say, sophisticated calculation. It's not applied to every case, but if you have a case like that, you can easily modify that. So when the time comes to do the output, you can see here, I can do total water, I can do actual water, and I'll explain what that is, precipitation, overbank, runoff, groundwater in. I also have the opportunity, and this may be something that may be applicable, to create my own time series and say, type 2 doesn't fit me. Ignore type 2, I will create my own time series from either normal somewhere else, and I will feed the model with my own time series. I call this user in. I can also do user out. I have measured how much water goes out. I will call that different time series user out. Like groundwater out, outflow, and so on. I will get back to this because that's a very, I want to show you basic stuff first, and then I'll get back to this because this is more involved. Okay. So let me do this. Let me start Wetbud. It's right here. So Wetbud will load. It will take a minute to load because it's a big program. The installation file is probably 800 megabytes because it has all the databases in it. Which model? We have calibration for web because we calibrate web. I showed you measured data and web. We have what we call hydro periods. I haven't talked about hydro periods yet. Hydro periods are actually measurements. And then we have a min and max. And then we want that. There's measurements. There's measurements. Measurements of existing, we have modeled existing wetlands for which we have actual measurements. And then we saw that this model actually can simulate those measurements very well. Not so much with the basic model, but we can do this very well with the advanced model. The advanced is even more sophisticated. Okay. So this is the screen that you get the main menu. So let's say you know nothing. You don't have time to read the manual. You want to do something very quick. So I will use this guy here with the magic wand. And this guy goes, okay, I'm ready to create a project for you. Do you want to continue? Yes, I want to continue. Where is your project? Okay, so I will select a known location. I will say negative 77.5 latitude and 37.5 longitude. Again, that's in the Virginia area. And the wetland, I will do metric. And my wetland bottom elevation is 100 meters above sea level. Okay. New project will be created. Continue, yes. The coordinates are outside. Okay, what did I do? 37. Let's take a look at what I. Try again. Doesn't like me. Okay. Okay. Yes, it's the other way around. So. Okay. 37.5. Okay. Yes. Okay. So it found that location. It found that this is in this area. And this is my my project. and this is the nearest weather station, which is the Richmond Airport. Okay. It has all this data. Then it says by default, I'm going to utilize the Thornthwaite method because that's the simplest method and it's there. I will use that. So you say, okay. Then how many square meters of wetland do we have? Let's say this is the watershed area. This is the green area, the blue area above the wetland that we want to define. So let's say 40,000 square meters. 1,000 square meters is 1 strema. This is 40 strema. Okay? Huh? 10 acres. 10 acres. Is there any constructed wetland? Is there any existing wetland there? 0. How much is the wetland I want to construct? I want to construct the wetland of 1 strema. Okay? So basically, my total wetland area is 1,000 square meters, and my watershed feeding into a wetland is 39,000. And the curve number, which is used for the runoff calculation, an average value will be 7. A new scenario will be created. So I have a project which has the location and the scenario that has different options. And this says, you cannot read this down there, but it has some initial parameters that it will use. I will show them in a minute. Basically, you can run the calculation because you have all the data are there. So I would say calculate water budget. It automatically determines that the dry year for that area is 1976. You use the dry year for the runoff calculations. Normal year is 1990. You use the normal year for the runoff calculations. Wet year is 84. Same thing. And then calculates all of that. And let me maximize this. And this is the water budget. So basically it says, I'm going to start the year in January. So all my graphs like that start January 1st and end December 31st. H, right? Yes. And I'm going to have 7 centimeters of water in my wetland in January. And I will have negative 33 centimeters of water in my wetland in August. What does negative 33 mean?
Dry.
Yes, so? Huh? It went below the saturation zone. 33 centimeters below the surface. So it has dried out to 33, but when it rains, it's going to fill this back up and then go high. Okay. Now, let me look. This is my dry year up here. Let me look at precipitation.
Should we need to be wet 9 months out of 12?
Yes.
From the previous figure, it didn't seem.
Right. So this is a design tool. You need to modify certain parameters to make it work. It doesn't mean that this is a solution. This is a design tool. You need, is your weir low, high? You're gonna, okay. So let's go to precipitation. These are the numbers that were used at time series of monthly values. This is the runoff that was calculated for these values. So that means in January, we had a lot of rain. It generated 20 centimeters worth of rain, worth of water input into the wetland from that watershed.
That's already accounted for precipitation.
It's right here. These are the individual components. The sum sums everything up. So ET in January, 0. There's no sum. ET in July, 15. Yes. Overbank. No overbank. Okay? Because the wizard by default says there's no stream there, but we can add a stream. Outflow. This is how much water we lost from the output weir. We lost 28 centimeters in January and nothing in between, and then it started raining again in October. We lost water there. Groundwater in, 0. We didn't specify in. User in, 0. Groundwater out, yes. The default value says we lose 2.5 centimeters per month of water constant through the bottle. Okay. And net water, loss or gain. So this is how much we lost. This is how much we gained. Actual water level. This has to do with the porosity of the ground and the saturation of the ground. Okay. So total water is mass balance. Actual water is actual depth. If you drill down, you will see dry horizon up to 1 meter below 1.3 meters below. This is for the dry year. What happens with the wet year? Wet year is a different year, different diagram. Total values, precipitation, a lot more precipitation. Look at the wet year, what happened here in March, okay? And it is the same or close to be the same because, okay? And outflow, different profile. So you need, going back to your question, you need, this is a very basic first pass to make sure things are working. But then you can tweak your model and say, I'm going to do this and this to make it work. Okay. Any questions so far?
Only about the wet, the normal, and the dry year. It's about, let's say, white swan. If we want a black swan case, we can, let's say, try to simulate it with this.
Yeah.
Maybe we can put in the user in,
Mm-hmm.
exaggerate values, and
Mm-hmm.
then
I'll show you how to do that in just a minute. Before I move on, I'll show you all of that for the dry wet year, for example, I can export in Excel. So if I click export charts, it will load up Excel and it will create, it's actually doing stuff here. It's creating charts in Excel. So you can get everything that you just calculated in forms of the form of diagrams and columns, data points. Okay. Okay. All right. So let's say, oh, and then I can do a report. Let's do a report, one report. So define a new report, go like this, yes, it opens up the report interface. And I want to generate a report for this scenario into a Word document. Okay. Let me close this and say generate a report. It says when you're generating a report, do not touch the keyboard. Okay. Because it's going to open up Word file. And it actually creates things in Excel, pastes them into Word, and continues putting stuff in Word, tables and things like that. So at the end, you get a full report with all your input data and all your output. And that report is eventually will be formatted to print on a portrait shape. Done. Report is here. Okay, so it has all the data in tabular format, all the assumptions that were made and so on. Report is generated ready. Okay, I'm going to close this. So I'm going to close that and close the widget. So basically what I did, I created a project which has the location, and then I created a scenario with what I just talked about. starting point and no overflow, no groundwater. So I can go to my basic scenarios, and this is the scenario I calculated. It took the default year for wet here in 1976, default year for the normal year, and so on. But I can say user specified. I can specify my own year. I can say partial year. I don't want the whole year. I want, or I can say I want my own custom period, 2021 January to February of 2022, 13 months. That's what I want. So I can specify my own. Then I can do here, go here, play again with the areas. I can use data. I can provide calculations for utilizing WEM. I'll show you that. I can specify my inputs. Groundwater in, no groundwater in. I use a constant rate. I use groundwater using WEM, or I use a groundwater time series. So I have measurements that say how much water goes into the wetland, plug those time series in, and do that. Same thing for overbank flow. No overbank flow, I can calculate it by Wetbud, use the time series on a monthly basis, use the time series on a daily basis. And if this is really getting tricky, I can do hourly basis, because stream may have better hourly values. And this is my user in time series here. Same thing with water outputs. I can use a variety of ET as outputs, variety of groundwater, variety of user out. My site parameters. I can tweak my site parameter. And this is my stream overflow. I can use the different channels, and this is my channel cross section. I can modify that. So there's a lot of, and I'm not going to go through this specific example for overbank, but there's a lot of options to fine tune. You may want to connect that to your stream to get more water in, so you have a better wet period, dry period. Okay, any questions so far? No questions.
I think just here before you move on, it's the big slide, the one that you can select the type and the way that it is formatted, it's called
The channel.
the channel.
Yes.
Trapezoid, or if it is.
Yes.
Yes, it's very important sometimes, depending on the type of stream.
So for example, here I can say I have a simple trapezoidal channel. And that's my stream. Okay. The channel has Manning's coefficient, if you know what that is.
Yeah.
It has channel width of 3 meters, slope to stream flow of so much, elevation of stream bed. You can specify that in 3D space.
This one, because it's very important, the shape of
It is.
in terms of the stabilization of the bounds, which is very important for technical.
Yes. And then, so this is the stream channel, and then you can specify the channel that connects the stream to the wetland, which is down here. It says inflow structure. So the inflow structure is the channel that connects. Again, you can specify that. Any other questions? Okay, do you want to take a short break? Bathroom break? And then we'll continue in 5 minutes.
Now, one comment during the break. First of all, it's great to see you back here, and thank you very much for this lecture. My hydrology and hydraulics level for my undergraduate year, okay, was sufficient to follow your work, which was very, very good. But one comment on the very first model that you showed, that all models are wrong, but some models are useful. This is attributed to Professor George Box. He wrote it, you said
Box and Draper,
but I think it's Box who wrote it in a little book or
Yes.
or a paper. But I want to say a few things about Box and Draper.
Okay.
Okay, now George Box was English. but he was a professor of statistics at the University of Wisconsin,
Yes.
one of the greatest statisticians of the 20th century. George Box. He's famous for many things, but he wrote very, very useful books. The first is on the design of experiments, very useful for all those who do experimental work. It's called Statistics for Experimenters. And the second is the time series analysis. He was the one who set all the basis for the time series analysis. And on the other hand, Norman Draper was also English, also a professor at the University of Wisconsin, and he's, among other things, famous because he wrote a standard textbook, the famous Draper and Smith Applied Regression Analysis. This is for the history of these two very great statisticians, and because this is the break, and there's another British extremely famous statistician, Professor Cox, from I think the University of Cambridge, who has received an honorary doctorate degree from the Technical University of Crete, maybe 25 years ago.
Okay.
And if you make the combination Cox,
The famous paper of organization, the famous paper, the only paper Cox wrote with Cox, the famous paper nation of observation.
and one of the statisticians we use it very, very often. And it has only one drawback. You cannot transform to non-distribution negative data. That's why with Dionysius we created a modified function.
Well, the reason I put that in there is this has a lot of statistics in it.
Yes, exactly.
So, I mean, we do a lot of transformations and fitting to the type 2 and the medians and all that. And but yeah, thank you for I thought it was Box and Dre, but it's George Box. Okay.
We may have to check it out, but I
Yes.
think it was,
Okay.
even Cox criticized Box for this mistake at some point.
Okay. So let me go back to the program and show you just as to have an order of magnitude. I'm going to go to existing stations. So this is a list of stations for which we have data. So for example, we go to the Richmond station that we have data from 1973 to 2014. If I hit a year here, select the year 2002, this is the monthly values for 2002, and these are the daily values for month 3. Okay, so all this data, and I can chart the annual precipitation for every year. I can export all this data. So all this data are already provided for specific areas. But for example, Andreas wants to do something somewhere else, right? So I will go here and I will create my own station. I will call my own station Andreas. All right. And I need to give it a latitude, Andreas. This is getting difficult here. So I will give it a latitude 38, I don't know, 60. And I will assign, I can go to not this one. I can go to the main database and see if there's a station nearby. So let's say Athens. There's a station in Athens. Yes, there's a station in these Athens are in the US, but this may be Greece. First one is Greece, Athens Observatory. Okay, Athens Observatory has data, very few data, 2001, 2001. So Athens, this is not a good location. Let's say, do we have Thessaloniki? Data in Thessaloniki. Okay. See if we have anything else for Greece. Orestiada, 1960 to 1978. So I will create a station for Orestiada in my local database. And if I go to my local database, here is Orestiada, and this is Orestiada, and now I will see if I can download data that are available from Orestiada from the web. So I can actually create my own database. Let's see if there's any data in Orestiada. So I go to precipitation, select Orestiada, I say web retrieval, download data. Okay, I found some data, and it's download. I will say okay. I think it's downloading every year. That's why it's taking so much time. 1962, so it would take a minute. I can also cancel it. Let's go. Terminate download. Okay. Import data. Maybe it didn't. But the idea is that you can download data and you can import, if there's data there and there's numbers, you can import data, so I can create my own weather station. So that, then I have to check if I have all the data points, all the months, have all the days and all that, and that will allow me to create start creating a database for my area of interest. And Michalis and Giannis created a station for which they imported data because they got measurements from somewhere else. The measurements were not available on the web, but they create their own measurements. And then, like here, for example, Andreas, I can go to my station, Andreas. But I did that. Andreas, and I can import from Excel. Okay. Okay. Same thing for ET data. So any one of these stations here, they will have preloaded ET data. Okay. So with these two main parameters, we can build any model we want. Okay. All right. Any questions? No question. So let me go back to the presentation.
Sometimes you may ask for the people online have a question.
I can do that, but
I would.
are there any questions from the audience? No? Okay.
Nice to hear what you confirmed that according to our experience, as you mentioned before with Michalis and Giannis, it's very easy when you download data from weather stations that we use national weather system to download the data, and also as Professor Giannis mentioned, you can do the corrections or any substitution of the missing data outside, and then you can import it. So it's very user friendly to do this sort of create your own station.
Okay, we talked about that. I have some slides here for the project wizard, but I showed you the project wizard. This shows basically here with the example that I showed you that go to the top. the different total watershed area. This is 10.5 acres. The existing wetland area is 0.26. The constructed wetland area is 1.74, which is the green area outside. Total is 2, and the watershed area, therefore, for direct runoff, which is a calculated field, is 8.5. 10 minus 2, 8.5. We go to the advanced model. Need to do that. Yes.
How do you define the borders of the watershed?
Go back. No. Okay, this is a watershed. Watershed means if you have a mountain and it rains, and the peak of the mountain is here, the water that's left of the peak would go on this side, and the water that's right of the peak. So you see this line here?
Yeah.
So that means if it rains to the left of this line, it's not gonna come to the wetland. It's gonna go this way.
Yeah.
So this is a peak right here. If it rains to the inside this perimeter, it's gonna. So there is a routine in ArcGIS, even what's the other the free package QGIS. The routine that say here's the topo, find the watershed, and will automatically do that for you.
How do you calculate the wetland?
Okay, so this project says, I already have an existing wetland here. You see that little green dot. And I want to expand this wetland right here. Because this says existing, new. New is 1.74, existing is 0.26. So okay. I think I have an example here. I did that. Okay. I just want to show you this slide. So I have internally, we have a huge database, precipitation data, weather data, temperature, wind, speed, viewpoint, and all that. Solar data. Solar data is used to calculate ET, and also ET data that have been calculated. And then inside the database, we keep also all the user time series, when data, and so on. And the basic models, the projects, and the advanced models with all the properties that we were talking about. And the idea is to have, if you're, for example, you're doing the project in OLBS, that's project. But if you wanted to do 2 or 3 different variations of that project, and say, I want to try a wetland which has 1,000 meters, 1,000 square meters, or a wetland with 2,000. That's scenario 1, scenario 2, because it utilizes the same overall parameters, but scenario 1 and scenario 2 are different. Okay. I know you want me to I can jump to the advanced model. Let me do that. And I'll come back to the basic model. Okay. So let me do this. So in order to do that, I will select a project that has an advanced model. So this is a database with a lot of projects. I will select a project that has an advanced model. Select and close. So this project actually has 13 scenarios under that advanced project. Okay. Scenario 1. These are my layers. Layer 1, I have my top elevation, my bottom elevation. Okay. I also have my ET surface elevation. So I know where my saturated, it has actually drained down to that elevation and it's dry above, but it's wet below that. Okay. Top elevation. It's not flat. So I click on top elevation. And these are the elevations for the grid. I have defined a grid above the study area. These are the elevations for the grid. And you can see the different colors which correspond to different, you can see you know, 109, 117, 125, 180. Okay. I can do the bottom elevation of layer 1. So I can now define for every cell the different elevations. I can do layer 2. But now the top elevation of layer 2 is the bottom elevation of layer 1. But I can do bottom elevation of layer 2 right here. So for every layer, I have a whole surface, which is basically, if I go to general, this has 69 rows, 102 columns, 108 columns, so 69 by 108, and every column width is 16 feet, about 5 meters. So 5 by 5, I define my grid, okay? And the time units here are seconds, whatever. I mean, you can specify that too. I can define a head for no-flow cells. I can define a head for dry cells, different, okay? So this is my setup. I can define my solver. I can define how precipitation is going to be treated if you have precipitation in neighboring cells top to bottom. How ET is going to be treated if you have how ET transfers from one layer to the next. Okay. So once I've done that, I can create the input mode flow. This will actually is the front end to mode flow. I can create the input mode flow files, solve mode flow, and then show the output, load the output into Wetbud and show the output. Yes. Yes.
So you can select, or you can.
Now, it doesn't use the regular solvers. Mode flow has, let me go to, no. Mode flow has a variant, which is called mode flow NWT. NWT is for highly nonlinear problems, and it uses that. Why? Because the top layer is water. We are simulating the top layer of water because there's flow in that layer. And of course, if you have an island that's sticking out, that's dry, but the rest can be water. So we're using the NWT solver, which actually converges because the 2005 solver doesn't always converge. Okay. Okay. I can actually go to jump to show you, because you also talked about calibration. So I'm going to show you. This is an advanced scenario. This is my rectangular grid. Gray cells are no flow zone. So there's no flow in this, but there's flow. This is my wetland. Random shape. This is not square. This is not rectangular. Random shape. And showing you that. This is how you define, for example, hydraulic conductivity. I have 7 layers. Sandy loam, sandy silt, whatever, forested, open water. So for each one of these layers, I have properties, Kx, Ky, Kz. In this case, all the same, but there's properties. I can put drains, that wetland, specific locations with drains. I can put a general head boundary. So there's water coming from the side, water leaving the other side. And I can select monitoring points. Now, the monitoring points are what make the difference, because I have a piezometer there or something that will monitor. So I say, okay, give me the flow or head at this point. And when I do that, I come up with something like this. This is my monitoring point. And this is time of step day, and this is head, okay? And this is the measurements. Okay, so monitoring is the red line, observed is the green dots. And I haven't connected the dots because sometimes they don't connect. Okay, measurements don't typically connect because you're going to assume what it's a line, it's a linear thing, and these two outliers. So this is how you calibrate the model. I mean, to run this is probably 2 weeks worth of full-time work. This is calibration. This is not more, I mean, this is, I'm not using multi-flow calibration.
But it seems like same similar tool when you do a calibration in one flow for the wells when you have the data and the measurement.
Yes.
But this is simply incorporated inside the.
Right. And you can actually see here, this particular case study had a number of monitoring points. You can generate graphs for every monitoring point. It will give you 2 statistical indices here, NSE and the root mean square error. So you can see how much your error is and so on. And you can export all these graphs and so on. Okay. Okay, let me go back to. Okay, this is a case study for the basic model. Okay. So this is the area that we wanted to study for a potential wetland application. This area is 89 acres. If you multiply that by 4,000 square meters, is a few 100,000 square meters. This is partially forested. You can see the forest here. And fallow means a field that's intentionally left unplanted. So these areas here were not planted in order to recover the soil, because we talked about soil. So there is considerations like that here. Okay. You need to look at drainage. Does the area drain east to west, north to south? Where does water go? This particular area also had a stream right here. See the stream. But also on this side, and you see the stream has 2 colors. You have the blue line, which is the center of the stream, and you have the brown area, which is the floodplain. Maria. So when the stream gets full, it will leave that center line and it will expand to cover the brown area. Okay. So water drains from west to east. Okay. Now, you need boots on the ground to find out the areas that may have potential for wetland construction. Okay. And Emmanouil is not here, but you do a series of test pits to determine the type of soil that you have underground. And this is actual work done. I didn't do the work, but others did the work, and this is what they looked at. Okay. Stream, they decided it's not worth looking at because of different things. And also, there is I'll show it to you in the previous map. This area has houses here. So if you probably want to prevent flooding in the stream because you're going to flood the houses. Okay. I was just saying that in this particular case study, you look at different areas and you also do a series of test pits to determine soil composition. So this is what this says. Do you want to create wetlands on the east or the west? Water flows from west to east. What are the soils? What do the soils look like? Do we have already pools of groundwater, water coming from below and pooling there because of soil conditions? So they decided to do 4 wells. They drilled, these are shallow wells, 10 meters, 15 meters. They wanted to see if there's a fluctuation in groundwater. Why do they want to see if there's a fluctuation in groundwater? Or if there's, yes. And there's an extensive clay layer in the potential wetland creation area. Is that good or bad? What does clay do?
Impermeable.
Impermeable. Okay. Having said that, when we do the basic model, let me go back to the basic model. I forgot to mention that. I go back to the basic model. There's an option here that says that says during goods. I don't remember where it is. Is there an impermeable layer? And if there's an impermeable layer, at what depth? So that prevents drying of the upper soil, because if there's impermeable, ET cannot go below that. Okay, so that is also, but I don't remember where it is. What the outputs? I really. Okay. Okay. Next thing is try to estimate KSAT. And they use their soil data to go to this triangle diagram, clay, silt. You can explain that to the group very easily. Let me do the trick here. And sand to be able to calculate the hydraulic conductivity value here, which was estimated at 3.9 times to the 10 to the negative 7 centimeters per second. So for this model, we have precipitation, yes. We don't have any groundwater because the groundwater level is pretty constant. We have surface water, yes, because it flows from west to east. We don't have overbank flow because the stream down there, we don't want to use that. We probably do a wetland further in. We have ET. We have surface water output for sure. Groundwater output. We have the KSAT for that. And then we can calculate how much we're going to get. And basically, they decided to do a series of smaller wetlands within that 89 acre land. And the way these were designed, this is the top and this is the bottom. The top feeds the second one and the second one feeds the third one and so on. So you model these as single cell wetlands. And then you take the output of that and you put it as input in the next one. Okay, so it's a series of wetlands because of the topography. Okay. Each cell has its own direct runoff drainage area. Outflow times surface area is the volume, and that volume feeds into the next one. Oh, I'm sorry. It's right to left. Yeah, it's the other way around. Yeah. Right. And then you can do that in the this is the output for the basic model. So you start with the basic model before you go into mod flow and all that. And you have all your parameters, you have your areas, you can guesstimate KSAT for groundwater out, no groundwater in, no overbank, and you can do this with the, this was actually close to the Washington Dulles International Airport, the main airport, the Washington area. Okay. And this is all the information. I'm not gonna go. And this is what you get for the normal year, and so on. Now, hydro periods. I didn't talk about hydro periods, but this is a good location, a good spot to talk about hydro periods. Hydro periods, you see this very light green line, and this is a light blue line up here, are the minimum and maximum water levels observed over a period of time for a specific location. So that says, I expect in this location very low water in August. But I may see also very high water in August. So my water fluctuation will be between this maximum and minimum. This also serves as a check to see if your calculations make sense. So if suddenly you had a peak here in the January, February timeframe, that wouldn't be logical. Okay. These are 12 hydro periods from certain locations that have been incorporated into Wetbud, but you can create your own. So this for this particular location, this is the maximum. This is given in inches, 5 inches of depth, 5 inches about 12 centimeters, 2.5 centimeters, and this is negative 35. So basically, your water budget can drop to negative 100 centimeters in July, August, and September for this particular area. Okay. All right. Any questions? Andreas. Designing for multiple planning community. But it's not my strength here. Okay.
I want to ask you about previously when you show us the areas for each wetland.
This.
Yes, here. I mean, okay, we have the overall, but then how we assign this?
So basically, from what they did, if I remember correctly, this has been a few years ago, they divide, this area has a distinct topography, and also it has,
Yeah.
right? So they said, I'm going to do this as cell, says cell 6 here, actually 7 and so on. So I'm going to design this as a standalone area for water budget, which means there's a berm here in between, but there's also a weir. So this here corresponds to a weir that will connect this to that. That's the only way water can flow from this to that. Here it's a berm, so water. I mean, if it's a flood situation, everything's flooded. Yes, it will flow from everywhere. But in the regular conditions, this is the watershed that will feed to that, and this will feed into that. And actually, I can see here there's others. This is cell 3, so it starts from up there. Maybe these were existing ones. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Any other questions? Okay. Let me talk a little bit about storage. So let me go back to this diagram. This diagram says, I expect my wetland to have a flat bottom. Okay. And therefore, I can, and again, the weir elevation, if it goes over this elevation, this is my average bottom elevation. If it goes over this elevation, water will go out. Okay. And this is my water surface elevation. And usually the weir will it will overflow over that. But this is my average water elevation. What if the bottom is not flat? What does that mean? That means if I have a pit here, a depression here, or like a small hill here, my volume is going to be different. So to compensate for that, I use GIS again to come up with what we call a stage storage curve. Stage storage curve means, go to this diagram, means this elevation of the wetland corresponds to so much volume. And as the elevation changes, this is not linear, not necessarily linear. As water fills up, then I can calculate the volume. So give me the elevation, I'll give you the volume. If it's a flat bottom, then it's a linear relationship. But if it's not a flat bottom and it has, then it's a non-linear relationship. So when you get the water elevation, and this is Beaver Run. So let me go to live. We go to a live project, select projects. So I can select a different project if I want to. Beaver Run, this one. And I go to my basic scenario. I will load the results because the results are there. And I'll go to, there it is. This scenario 6 has data for water elevation. It should. So as I move along this line, it will give me, see how the bottom crosshairs moves? It will give me how much water I have. Let's see if I do total water. Yes. If I'm here, this is how much water I have. If I drop, now if I go off the diagram, it's a different story. But it will give me, based on this line, how much water I have. So at this elevation, I expect my wetland to have so many cubic feet of water. Okay. Any questions? No questions.
Stage here that you just showed us, it's a separate one for each month. Okay, big one for the areas.
Yes. Basically, okay, that's another good question here. Under parameters in project-specific data, specific to the project, because these parameters here are general, precipitation for all stations. Under project-specific parameters, I can have my groundwater, my user, depth to water table, stream data for geometry and flow, depth to weir, if I want to have a variable, reference hydro period, stage storage curve data. So this is my stage storage curve, these are my values, this is my data chart, but I could create another one. Say I will assign that to this and that to that. So this is mainly topography driven. It's not precipitation driven.
Yeah.
Based on the topography, how much water you get. Okay. And again, all these mining coefficients, you can define your own. Depending on what you have, you can get different coefficients and so on. It has a lot of options, but I showed you just scratch the surface so that you can, if you want to use it, to know where to start from. But basically, the most important thing is have good, clean data. That's the most important. Okay, any other questions? Yes.
Don't mind one general one. You you showed most of the presentation was the more mechanical and engineering aspects of the issue.
Mhm.
If you don't mind me asking about the more sustainable and biological aspect. To me, it seems that this is some sort of like a terraforming of the ground you're building these wetlands. So I'm only asking, do you also take into consideration that the environment which you're creating there, is it sustainable for the environment, to the region that is done? But to the essence that you take insects and you bring a water source, which previously did not exist.
Okay.
This is done by artificial means.
No, yeah. Let me show you this slide again. That shows what is the driver behind Wetbud. Okay. So if suddenly there's an area here in Akrotiri that is a wetland.
Yeah.
And I'm a farmer and I know I own that area. So I say, okay, I'm going to get rid of the wetland and I'm going to grow horta. Okay. Then the area lost the wetland. In Greece, nobody's going to say anything. Fine, this is your own area, do whatever. The US, they would say, well, you destroyed a wetland. Somebody needs to create an equivalent area close by. So you're not introducing new stuff, you're restoring what somebody else destroyed. To make it simpler, the new national road that will go to Kolibari needs to go over wetland because there is a wetland there. So now the government destroyed the wetland. So somebody needs to create, in Greece, that's fine, wetland is gone. In the US, they would say, okay, you need to create a wetland nearby that will restore the habitat for these creatures or whatever in the vicinity.
So what was a pre-existing thing? It's not that we artificially made this and sustained this through artificial means.
Wetbud was
Sorry, a wetland, forgive me, a wetland. It's not something that we sustain through artificial means, it's something that was happening naturally, but we
Yes.
advantage of it.
and we need to design a wetland which will sustain itself naturally. That's the point of wetbud. Before people would say, okay, I'll create a pool and throw some water in there and that's fine. That's not a wetland. So this was designed so that people that are in the business of restoring wetlands to do it properly know the hydrological side. So this was designed, this group here, if I go back to the people that worked in this project, this guy is a soil scientist. This guy, Rich, is a hydrogeologist. She is a surface water person. So they all had to do with water flowing in different areas. And they saw that and actually the people who funded this, they saw that a lot of work was being done, but if the wetland goes dry, you spend all this money and effort, and you use a land and then the wetland doesn't work, what's the point? You have to do it again. So that's why they came together and they said, let's create a tool that will allow people to create a wetland that can actually, so Julie Metz, for example, this wetland right here, they put it together back in 75 or whatever. Look at this now. They don't do anything to it, just self-sustained. Any other questions? Yes.
So more or less, we put in our model things like precipitation of water, and we see if the wetland will be sustainable.
Yes.
So here that wetland gives us that everything as it is sustainable as a wetland.
What do you mean as it is?
I mean, I take the rain, the precipitation that drops in the area, the outgoing, the ingoing, as it is, it's a case, it should be sustainable as a wetland. Why did it not already be a wetland if the conditions are perfect for it to
First of all, good question. First of all, let me go back to that diagram that shows the conceptual wetland. this diagram here. Okay. Are you going to connect it to the stream or not? How high is going to be my outflow here? It's going to be this high, this high, this high. This is what the different scenarios will let you do. And actually, there is a function here. If I go to basic models, and I'm looking at that, see here multiple scenarios. It will allow me to compare scenario 1 and scenario 4. See how very different they are? Which one should you, different design, it's the same area, different design characteristics. Where is different, is connected to the stream, is not connected to the stream. Okay?
So also, if
this is open water features. Different. This is groundwater, with groundwater.
if I use this, in order to validate, more or less, if I take one working, one you said that they put a pool there and maybe it is.
I call this the bathtub effect. You can create a bathtub very easily. You get one of the civil engineers, you pour a lot of concrete, and you create a bathtub. That's very easy. That's not what we want, right?
Yes, but if we use that to validate an already existing wetland, how accurate mode flow would be? If, for example, I use it in 30 different sums, would it tell me in 80% of the cases that yes, this is a wetland?
Mode flow will not tell you if this is a wetland or not.
Not mode flow,
Wetbud. Wetbud will not, what Wetbud allows you to do is to come up with distribution like this. Very, very correctly, you pointed out that, this is dry, 0 is up here. Basically, this is wet 4 months of a year and dry 8 months of the year. This is what Wetbud allows you to do. Try different designs until you get a curve that matches your specifications. My specifications are 6 months dry, 6 months wet. Does this match it? Yes. Your specifications for a different area because it's northern, it's more sunny or whatever is 3 months wet, 9 months, whatever. So this will allow you to match your specifications to the site, to the design, not the site, to the design.
Very well, but I'm asking this, okay, after the design, and we do it, does it work well, and how well? I mean, okay, I can also put some nice equations, like code, and say, it will be dry in 9.
If you want, basically what you need to do to validate this is measure the water level.
Yes.
So you need to have if it's above the surface, you need to have a floating system to measure water above the surface. If it's below surface, because it gets dry, you need to have a way to measure. I mean, there's a little PVC pipe and a floating device. You can measure the water level below surface.
So it's easy to validate.
Very easy. Yeah. Yes.
One more question. So what if we will have, let's say, an existing lake or an existing pond? It doesn't work as a wetland, but we want to convert it to wetland. The basic difference is that the wetlands, we know that they're quite shallow.
Right.
So this is why wetland.
So basically, you need to create an opening for the water to drain and see if that works.
I'm thinking about the input and the output. It's pretty much, yes, we can understand. Straightforward. And if there's also a river nearby, everything about the wells and everything. What about the depth? If that's the depth of, let's say, if we have in the lake, it's like 1 meter, 1.5. Is it like this is something that the Wetbud will take it as a problem, or because of the depth? Should it be always shallow, or?
So Wetbud will need the average bottom elevation if your elevation is 1 meter, I mean, if the bottom from the surface is 1 meter, this is actually regulated by the weir.
Okay.
So if you lower your weir, your gate, then you can drain.
Water, so you can
It will have a steeper bank,
lower,
but you can drain.
so you can control it from the where, how the depth,
Yes,
or how.
provided you can drain it from the weir in a natural way, because if the
Yeah.
pond is here and there's no way for the water to go out, you cannot use it.
No, definitely you need an input and an output, so you can adjust to the where the depth of
How much water remains in the,
yes. And then you can see signally, as you explain to us, you will take account the runoff, you will take account if there is an overflow from a nearby river,
Mhm.
and also the connection from the groundwater
yes.
based on the different routes. So we can, let's say, consider it as a tool to transform an existing pond or lake to design a hydrologically operate functionality
Mhm.
of the wetland that will actually help the ecosystem
Mm.
as well.
Mhm.
This is really important, I think. Yeah.
No, I think you can also, going back, I don't remember your name. Evangelia. Going back to Evangelia said before, you can model any system that has has boundary conditions that are defined by city limits or mountains or in and out. It's very easy to do that.
Yeah, I was just having in mind if the depth, if as like depth, a specific depth of a specific of range of the depth of the lake or
Mhm, mhm.
the wetland. But yeah, you can control it as you mentioned. So yeah, you can model it as you want.
Yes.
So the code has no problem, having, let's say, a depth of 10 meters.
That was actually,
Yeah.
I haven't tested it. Now, when Yanis and Michalis did their diplomatiki in the metric system, we discovered a few bugs which I fixed because it wasn't converting a few things. I haven't tested anything to that extent, but if you run it and you see problems, well,
Okay.
Yeah, I have a question.
yes.
Does Wetbud build in the future JS function?
Say that again. Do what?
Wetbud. Build in the future JS tools support.
GIS tools.
Yeah.
Yes. Actually, it does. When you do the advanced model, let me select the thing that has. When you build the advanced model, there is a grid setup wizard here. And it utilizes a coordinate file, a coordinate grid file, which is actually something you export from GIS. So you can use XY grid from Excel and see this here, ARC, that's the ArcGIS, and you can bring in the file and it will import your grid definition. So it doesn't, you need stuff from the GIS program you need to create those in a GIS program, export it, and then bring it here to define your grid in it.
So it files like this, CSV shape files.
Yes, shape files.
It's good because
Yeah.
you have most of.
It can create a shape file. Yes, you can read the shape file.
Another way to connect to JS.
No, that's about it. You can also use a shape file. You can use GIS to determine your watershed. And you can use GIS to determine but then you have to bring that in. Shapefile is the best way to bring special information into this. So because the GIS uses other parameters for, but it will read a shapefile.
To come back to my previous question, that I actually mentioned this specific tool, if we can transform an existing pond or lake to a wetland, is that basically like there's some options for big lakes that are created in mining areas. Instead of it just
A lake?
if there is a nearby river, or you can create a channel that you connect, you can feed it, you can feed the lake, the big lake, and you create an outlet as well. So
And then you can plant things in there to clean it up.
it's exactly it's a reclamation area and a reclamation plan for waste-to-waste solution.
Very good.
So it's something that also we see in different projects, and it's a good option. And you can have a design tool to see if what you, according to the hydrological conditions of the area, if this is possible to do it, because sometimes it's not. If we don't have the right hydrological conditions.
I'll tell you a very sad story. There's a natural lake, there's a pit lake in northern Minnesota, or I don't remember, Wisconsin, somewhere there. Very close to an old iron ore mine, which creates acid mine drainage. The pH of the lake is huge. The pH of the lake is probably 3 or 2. That lake is used by migratory birds, ducks, that fly from north to south on the way back. So the ducks see the lake and say, this is a good place to land. They sit on the water and they die because it's acid. So they have a group of volunteers during the migration period that are obviously dressed in, protective gear, that they shoot guns and air cannons, to prevent. We had an air cannon system here for the pigeons for a while, to prevent the ducks from landing into the lake, so that they don't die. Yes. Unfortunately, that's a huge lake, and there's nothing. I mean, you can neutralize the acid, but the amount of material that you will need for neutralizing the acid is going to be huge. So yes. And if you let that water go without neutralizing, it's going to destroy stuff down the.
They have to keep it there.
But I'll tell you another thing, which is a natural thing. You heard of Rio Tinto? You know what Rio Tinto means? Yes. Red River. Why? Rio Tinto started from the iron ore belt between Portugal and Spain. It was a natural river which was red because of acid mine drainage, not from mining, but from the iron ore. So fish or whatever life was there was used to living in a pH of 3. So Rio Tinto means Red River because of acid. Yeah. So things can adjust, but when it's man-made, it will take them a while. Andrea, you want to go swimming?
For the way. I mean, hundreds of ducks, their feathers already outside the water. And just the way, scare them away instead of gathering the.
You're going to eat that meat? I don't think it's a good idea.
Well, it's only boy. Oh, no.
Okay, any other questions?
Small, again, general one. You said at the beginning that such a. Another water system, sorry.
You want to go back to?
Give the exact name, but the water mass that we want to create, I think it was, the environment you showed in the picture.
This one?
No, yeah, that one. So this you said those are used to clean, neutralize the waste.
The application we did actually it was the Hellas gold mine in northern Greece. The application, Hellas gold uses some reagents. The idea is, can we use a wetland to absorb metals from the wastewater so that when it's dumped where it's dumped, it doesn't pollute the wastewater. That is used, that's a method, well-known method used called phytoremediation. Use plants to absorb metals.
But this method, given that nothing disappears, so when the plant consumes this.
Very good question. Very good question. I'll tell you a story what the Germans did. The Germans had coal mines. I'm not talking about lignite, I'm talking about hard coal mines, which is used to create coke, C-O-K-E. Know what coke is? C-O-K-E.
Went to think further.
Yeah.
It's industrial.
It's coke is used as raw material for steel making.
Yeah.
So you take all the volatile matter of coal, and you create something which is pure carbon to use for steel, because steel is basically iron and carbon. Okay. So when they shut down the coal mines, they had shut down the coking industry. Now the coking industry, to create coke, you basically heat coal up, very high temperature, all the volatile material goes out, and then you pour water on it, like through a shower system, to cool it down. When you do that, all the heavy metals actually are drained from that coal into the ground. So when they were ready to shut that plant down, all the ground around it was polluted with heavy metals. Heavy doses of mercury, cadmium, all the good stuff, so that you glow at night. Okay? So what they did, they planted trees that have the ability to absorb. So they cleaned the ground by planting trees everywhere. Then they harvested the trees, they burned the trees in a controlled environment, and they took the ash. So they had all the heavy metals concentrated in that ash from the trees. So they used the trees as collectors, and then they burned the trees to basically decomposed that organic matter into organic and inorganic, and they collected the metals.
So the point, I assume.
The point is the same. Once you have cleaned the water, you will let the thing drain, harvest the material, and dispose of it. Now you have all the metals somewhere where you can control them.
Now you have, according to the law, hazardous waste.
Hazardous waste.
Yeah.
Specific specifications. You cannot store them in the normal landfill. Specific landfills with specific specifications that you can store the.
But the main idea is concentrated, because if it's in the ground or in the water, I'll tell you another related thing. I'm not going to talk about it tomorrow, but acid mine drainage, so solutions, low pH solutions that related to mining or even not mining, have a lot of critical metals in. Very small amounts of critical metals. So they have created a methodology by which to filter pregnant solutions that have low level of metals like that, and remove the metals from the solution, and then clean the water and let it go downstream. Expensive solutions, but they do it because they want the critical metals. Won't do it to clean the environment, but the side effect is that you clean the environment.
And does the time that, again, going back to what you said about, let's say, the trees, or in the same manner of speaking, does the time that it takes to collect such
it may be a longer time than, but it's free.
But is it sustainable in the long term?
Yes, yes, yes,
It's much cheaper, it's much better for everybody
Yes.
involved.
yes. And once, if you're not done, you harvest that first batch, you plant more, and you let it do it again.
Any risk of this, let's say, body of water escaping and creating further hazards?
Well,
Tornadoes and such?
you have to plan for that. That's why everything is when you do when you design water systems or any other systems, you have to design for 50-year flood, 100-year flood, 1,000-year flood. You need to do that. If you don't do that, I don't want to talk about Greece, but I'm going to talk about Greece. There's certain areas, for example, behind Elefsina, every few years the thing is flooded. Why is it flooded? Because there is a small river there, stream or Rema. They have built on the Rema. So what's going to do? It's going to flood, of course. The solution there is not to build. I mean, don't build. Okay. Anything else? I've covered, I mean, I can go into detail in anything you want, but I think it's going to be too much.
Okay. And we have also many, to be honest, people that follow those live, so really nice. Have people online also through Facebook as well. So thank you, Professor Agioutantis, for your presence, your time, and the effort to give us this presentation. I don't call it lecture. Presentation, seminar.
Seminar.
Yes, seminar.
Seminar is a good.
Really important to us, and it learns something new. And so thank you all for being here. And see you soon. That's all. Very much. Sorry,
Thank you.
I don't know if someone from the I don't know if someone from the online participants wants to mention something. That's before we go.
Yes, I would like to
Professor
thank
Varouchakis,
Zach.
you are muted. I don't know if
Can you hear me?
Otherwise, we will have feedback.
Can you hear me now? Can you hear me now?
Okay.
Professor Varouchakis, you can work it now.
Okay. I would like to thank you very much, Zachos, for the very interesting presentation.
You know what? The sound goes to the TV.
Can you hear Emmanouilis?
Goes through the HDMI. So, volume control.
Καλή.
Ναι, εγώ σας ακούω πολύ καλά. Εσείς με ακούτε? Great. Okay.
Ωραία. Τώρα σας
ακούω.
Go ahead.
Okay. I would like to thank you very much, Zachos, for being here and for giving this lecture. It was very interesting, really very interesting, and especially useful for our postgraduate program. Not only for postgraduate, of course, for all of us, because it was something new. We are running a lot of research projects that has to do with reclamation of several sites in Greece, and I think this tool will be very useful to be included in this project. I have already talked with Emmanouilis how we can, let's say, include this very useful methodology, this very useful tool in our already running project, because I think it has great potential. Thank you very much again, Zachos.
anything you need, I work closely with Manoj and you, anything you need, any further information, I'll be happy to provide.
If you can hear me, I just want to say that I've already developed two agricultural pieces, so we're very happy that we have even a small know-how for this tool, and we're planning to expand it to the MSc program. That's why all the students here to learn and to follow the seminar, so they have another choice for to select for
Different topic and so on,
topic
yeah.
for their statistics. And obviously, as Prof. Varouchakis mentioned, it's always an option for us for reclamation sites in the mining areas, and that's why I mentioned before one of these options that we have for the search projects, especially with the.
And even, Michali, the areas in Ptolemaida and Kozani that are being rehabilitated now, I'm sure.
That's why I mentioned the big lakes.
Yes.
That's what have in mind.
Okay. Sounds good.
Nice. Okay, so thank you very much all. Be around.
Okay.
Bye.